Hello and welcome. In this video, we're going to look at how to calculate duty cycle from a waveform. In the first waveform here, we are given a time value on our x-axis in milliseconds. And so we'll use that in our calculation for duty cycle. And we know duty cycle is actually our time on for the signal divided by our total time, our period for the signal, multiplied by 100 so that we get a percentage, which means that our duty cycle is always a percentage value, a percentage of time on specifically. We use this for driving motors and that kind of stuff. So we have to begin our duty cycle calculation by figuring out what our period is or our time on. And so let's start with our time on. We'll say that our time on begins when our signal turns on, right? So that happens at our 1 location here. And so we'll count from that location until our signal turns back off. And we'll see that happens all the way down here at the 6. And so that gives us 1, 2, 3, 4, 5 milliseconds. So we'll say that our T on is equal to 5 milliseconds. And we can do the same thing for our period. We know that that's going to be our total time in our circuit here. And so we'll go from the time it turned on and we'll keep going until it turns back on again, right? When the rising edge hits again. So we'll say that's 1, 2, 3, 4, 5, 6, right? 6 milliseconds. And that's going to be our T value is equal to 6 milliseconds. And so now we can replace our equation here. We can say that we have a duty cycle of our time on 5 milliseconds divided by our total time of 6 milliseconds, and that's multiplied by 100 so that we get our percentage out. And note that these milliseconds will cancel out here. We know that the millisecond on top and the millisecond on bottom, those two are going to cancel out if we divide them. And so we'll just be left with a 5 divided by 6 multiplied by 100. Right, and that gives us an 83. So our final answer for the first duty cycle is 83.3%. Right? That's the percentage of on time out of our full cycle. Right? But note the time here. This time factor is going to be our frequency. Right? Okay, so let's move on to the next one. We'll come back to that. So in this second one here, we do the same thing. We want to look at when our signal turns on, and that happens at this 2 location. And so from there, we'll count until we see the signal turn back off. So that's 1, 2, 3, 4. And we'll say 4 is our T on. And that is microseconds, right? So microseconds. That's much smaller than the last one. So we'll do the same thing for the next one, except for we're going for our time this time, so our T. And that happens when our signal starts to repeat again. We'll see that way over here. That's going to be our T value. So from our initial starting point at 2, we're going to go 1, 2, 3, 4, 5, 6. Right? That equals 6 microseconds. Okay. So we can plug that into our duty cycle equation. Duty cycle is a percentage equation. It is our time on 4 microseconds divided by our time total, our period, 6 microseconds, multiplied by our 100 to get our percentage out. So we'll do that here. Note that those microseconds will cancel out. So 4 divided by 6 multiplied by 100, 66.6. 66.7%. Right? That's our time on for this one. So if these two actually had the same, if this one was milliseconds and this one was also milliseconds, this would be the same frequency, right? They're not, because this one's microseconds down here, but the frequency between those two, if they were matching, would be the same. The duty cycles would still be different. And so that's going to be 2 different factors that you get to keep track of within these digital signals here, like these on-off signals. Right? Let us know if you have any more questions.